Sarah said, we're going to be talking about an introduction to ultra-high performance concrete. So these are the AIA required learning objectives that kind of make up the outline for this presentation. So at the end of this program, you should be able to define ultra-high performance concrete, recognize the differences between UHPC and normal strength concrete, and give examples of advantages and disadvantages of using ultra-high performance concrete or UHPC in the concrete industry, as well as describe the existing and possible applications of UHPC. So the outline for the webinar today will include an introduction of the UHPC material, some of the material background information, some of the advantages and disadvantages, as well as some existing and possible future applications for ultra-high performance concrete. So it's easiest to categorize UHPC in terms of its compressive strength. I mean, that's how we kind of categorize concrete in general. But the high strengths alone are not the only thing that defines the material. The ultra-high strength is just one of the properties that makes it ultra-high performance. So UHPC can generally be defined as a class of concrete that combines the ultra-high compressive strength with other properties superior to conventional concrete, which would include high ductility and durability. So UHPC was originally developed in Europe in the early 1990s. Now, two French contractors, and I'm going to murder these names, Eiffage and Bouygues, they merged with Sika Corporation and Lafarge Corporation, respectively, in order to develop an ultra-high performance concrete based on several established goals. And those goals included mechanical property improvement, optimized gradation, accelerated pozzolanic reaction and hydration modification, increased ductility, and trying to keep mixing procedures as similar to conventional concrete as possible. Now, Eiffage and Sika created a patented UHPC mix called BSI. Bouygues and Lafarge created a patented mix called ductile. Now, these two UHPCs exhibit similar properties, but BSI is known to be a coarser mix. Now, design recommendations have been created in Australia, France, and Japan for ultra-high performance concrete. But in the US, the material is really in its infancy. So this table just displays some typical constituent proportions of the ductile brand UHPC with metallic fibers, as compared to some typical constituent proportions for normal strength concrete. Now, there are a lot of different UHPC mix variations in existence, but I'm going to be referencing the ductile brand, which is marketed by Lafarge during this webinar, just because it's the only commercially available UHPC in the US. And Lafarge distributes it as a pre-packaged mix. They mix the dry constituents, the sand, the cement, the ground quartz, and the silica fume, and then provide that with the super plasticizer and the metallic fibers as a pre-mixed material. So also for the purposes of this presentation, when I talk about normal strength concrete, I'm going to be referencing concrete with strengths between 3,000 and 6,000 psi. Now, the one I'm showing here just happens to be a 4,000 psi mix. So as you can see, UHPC is comprised of many of the same materials that are commonly found in normal strength concrete, such as the cement, the sand, water, silica fume, and super plasticizer. It also contains ground quartz and fiber reinforcement. So here I'm showing a typical normal strength concrete mix without admixtures such as silica fume, which would reduce the amount of cement necessary, and without super plasticizer, which would reduce the amount of water necessary to achieve equivalent workability. So you can see the large difference between the constituents of this UHPC mix and the constituents of normal strength concrete, in that the UHPC doesn't contain any coarse aggregate. And actually, the sand is the largest particle size aside from the metallic fibers. The UHPC contains nearly double the proportion of cement when you look at the percent by weight. And actually, if you combine and look at a total binder content, if you combine the silica fume and the cement in UHPC, it contains over 2.5 times by weight the amount of binder as in normal strength concrete. Though the cementitious material content is so high for UHPC, it actually contains less water by weight. So kind of as a comparison as well, I included the particle size of the dry constituents, and I tried to arrange them in order of decreasing particle size. Now when you look at normal strength concrete gradation, it's important to note that combining different sized particles is going to reduce the void content in concrete. In normal strength concrete, we're normally combining 3 particle sizes: the coarse aggregate, the fine aggregate or sand, and the cement. Now in general, the larger the coarse aggregate, the less cement required. However, larger particles tend to produce an increased number of microcracks between the coarse aggregate and the cement paste, which is why in higher strength concrete, the maximum aggregate size is normally limited. Now in UHPC, the use of the coarse aggregate is completely eliminated, and 2 additional finer particle sizes are incorporated: the finely ground quartz and the silica fume. Now doing that will optimize the particle packing of the constituents so that you have very few voids present in the material. So if you pull the numbers for binder and water content from that previous table, and you take a look at the ratios of binder to water, you can see how little water the UHPC contains relative to the binder content. So if you just look at water and cement, the UHPC has a water to cement ratio of around 0.2, which we can all recognize is very low, whereas the reference concrete, the reference normal strength concrete, is going to have a water cement ratio of closer to 0.5. If we then look at water and cementitious material, or total binder content, the UHPC is going to have a water to binder ratio closer to 0.15. So what does that really mean? Well, with a water to binder ratio that low, we'd assume that we'd end up with a lot of unhydrated cement particles, and that assumption would be correct. Now, it's not necessarily a problem. It essentially means that the unhydrated cement particles are going to act as aggregate. So I wanted to show this SEM image of UHPC just to give you an idea of exactly how much we have in regard to unhydrated cement. So the white particles you can see that are labeled as A, all of those white particles are unhydrated cement particles. So I previously mentioned that UHPC exhibits a number of desirable performance characteristics, including the ultra-high compressive strength, high ductility, and durability. So to achieve these desirable performance characteristics, one of the things it requires is a pretty complex and controlled mixing process. So the best results are achieved with the use of a high shear capacity variable speed mixer, which really, that just means it's a mixer that can operate at high speeds, so you can blend and break up the cement particles, but it can also be slowed down to allow for the addition and proper dispersion of the other constituents. Now, it's not to say that UHPC can't be mixed with ordinary pan or drum concrete mixers. This has actually been done successfully in research and in the field. Doing that might result in a longer mixing process and thus an inferior distribution of particles and less optimum material properties as a result of that. A longer mixing time can also increase the internal temperature of the mix, which is another item of importance when mixing UHPC. Higher temperatures can result in decreased workable time. So both the temperature of the surrounding environment and the internal temperature of the mix itself have to be monitored to ensure the best possible product. Now an interesting thing about mixing this stuff, and I've worked with it myself, is that they don't really tell you how difficult it is to work with. To have a contractor work with this, you'd be pretty hard pressed to find someone who'd be happy to. I mean, you get the material mixed together, and if you start working with it with your hands, you've got small diameter steel fibers distributed throughout this mix. You can use a heavy-duty, thick rubber glove, and those fibers will still go through it. I mean, I've cut my hands through rubber gloves, so it's just kind of an interesting part of that process. So the addition and modification of the constituents in UHPC, as well as the controlled mixing environment, both result in the improved mechanical and durability properties. So to further improve on those properties, several accelerated thermal treatments have been explored for ultra-high performance concrete. It's been found that the ideal curing method, which is commonly described as the standard thermal treatment, that will result in the ultra-high compressive strength and the other desirable material properties in the material, consists of a 48-hour cure at an elevated temperature of 194 degrees Fahrenheit and 95% relative humidity. Now, this is administered after the material has achieved final set at room temperature and after it's been demolded. Now, allowing the UHPC to achieve final set at room temperature ensures that primary ettrinite formation will be completed before the material is subjected to the elevated temperature cure, so that delayed ettrinite formation isn't going to be a concern. So another commonly implemented curing method is to use varied onset timing for the thermal treatment or delayed thermal treatment. Now, this is one of the curing methods that's designed kind of to mimic a precasting environment where you might have several girders cast at one time, then they need to turn the beds over, so maybe they move those girders into a warehouse. They do that several times, and then they want to thermally treat all of those specimens at the same time. Therefore, you might have specimens of 3 days age, 7 days age, however many you might end up with. So a lot of studies have looked into what effect delaying that thermal treatment has on the UHPC material. Another curing method that's commonly implemented to kind of mimic precasting environments would be a lower temperature thermal treatment. So most precasting facilities are going to have the capacity to cure at temperatures closer to 140 degrees. So studies have been done to look at what effect it has on UHPC, both to cure at that lower temperature and as well as when you cure on that lower temperature. A typical precasting bed, they'll cast the girder, they'll ramp up to 140 degrees over a few hours and then ramp down subsequently immediately after that, instead of waiting for initial set before they up the temperature. So another commonly implemented curing method is just to allow the material to simply cure at ambient or air temperatures. Results obtained for UHPC cured in this fashion serve as a contrast for the effect of thermal treatment. Now, it's been found that specimens cured at ambient temperatures tend to exhibit compressive strength around 33% less than the compressive strength achieved with the standard thermal treatment. So all the curing methods I mentioned, aside from standard thermal treatment, are essentially designed to investigate the effects of more realistic conditions for the use of UHPC in the field or in a precasting environment. Now, again, the standard thermal treatment is ideal to achieve the most desirable properties in UHPC, but it's really only attainable in a controlled environment, and it imparts higher cure temperatures than are standard for precasting facilities. So to give an idea of the role that curing regime plays on compressive strength in UHPC, I just wanted to show some data for compressive strength gain of cylinders for both ambient cured specimens and specimens subjected to standard thermal treatment. So this chart shows data depicting compressive strength gain of cylinders allowed to cure at ambient temperatures. Now there's a couple of important things to note here. One is that the in-mold time differs with each specimen group, as noted down in the legend, and that varies from a 1-day in-mold cure to approximately 3.5 days. The other item is that if you look at the data by Grable, that's the data shown in red right here. Now those specimens were actually mixed in an ordinary pan mixer, which resulted in an increased mixing time and likely an inferior distribution of the particles. So that's likely part of the reason, or the whole reason, why those seem to be a bit lower than the cylinders tested by Nyland, Poyce, and Kohlmorgen. Now, those 3 specimen groups were actually all mixed in the same lab with the same high shear capacity variable speed mixer, and which, like I said, it's what is recommended to properly disperse those particles. So if you exclude Grable, you can see a fairly typical shape for strength gain curve over time in concrete. It's approaching a maximum value for compressive strength, which we would estimate between 18 and 24 KSI at 28 days from casting, going by this chart. So now if we look at specimens subjected to the standard thermal treatment, again, we need to note here that a couple of important things are the in-mold time differed, and that it varies from 1 day to 3 days, again, as noted in the legend. Now, going along with that, as they were subjected to this thermal treatment, each cylinder, say we look at Grable, those were demolded at 1 day from casting. After that 1-day in-mold cure, they were immediately subjected to the standard thermal treatment. And the same thing with Poyce. After that 3-day in-mold cure, they were subjected. So all of these cylinders were subjected to standard thermal treatment at different times. So, and again, the cylinders by Grable were mixed with that same ordinary pan mixer. So he had the increased mixing time, and it likely didn't result in the best distribution of the particles. Poyce, Kohlmorgen, and Mission all mixed their samples within the same mixer in the same lab. So again, that likely explains why Grable varies somewhat from the other sources. So overall, what we can see from this chart is that after thermal treatment, UHPC can achieve compressive strengths in the range of 28 to 33 KSI, and it doesn't really exhibit noticeable further increase in compressive strength over time after thermal treatment's been applied. So this table just includes typical reported properties for UHPC that has already been subjected to thermal treatment. So for comparison, some typical ranges for these properties in normal strength concrete have also been included. Now, some of the more interesting material properties of UHPC to note include the compressive strength, which is on the order of 4 to 10 times that of normal strength concrete. The flexural strength at around 7 to 30 times that of normal strength concrete. Now we can relate that flexural strength with tensile strength, which we all know that we normally neglect for normal strength concrete because it's so minimal. But the fiber reinforcing in UHPC allows for some significant strength there. The freeze-thaw durability of UHPC is near 100%, and that's due in part to its low porosity, and that's as compared to 80 to 90% durability for normal strength concrete if air entrainment is employed. Now, creep and shrinkage properties of UHPC are also drastically improved from normal strength concrete after heat treatment. So I've already kind of discussed several of the factors that are going to affect the properties of UHPC, including the constituents and their proportions, the constituent gradation, which is going to affect the particle packing, the mixing methods, and the curing regime. Now I'm going to take a look at some of the material properties of UHPC and correlate the primary effects of each of those factors on the material properties. So the properties that are going to be primarily affected by the curing regime include the compressive strength and the elastic modulus of the material. And that's due to the increased hydration and pozzolanic reactivity caused by the elevated temperatures. The shrinkage, not the amount of shrinkage exhibited, but the time at which shrinkage occurs. Now it's important to note that the small amount of shrinkage noted in this table is post-cure. UHPC will shrink no matter what curing regime is employed. Now shrinkage is expressed as unitless strain, and it's going to increase at a decreasing rate over time, eventually approaching an asymptotic maximum value. Now subjecting UHPC to thermal treatment really just speeds up the shrinking process due to the consumption of the free water in the cementitious matrix and the increased hydration rate. And that allows the material to approach that asymptotic maximum value for shrinkage prior to the completion of the thermal treatment. So the post-cure shrinkage is very low, not the total shrinkage. Now creep in concrete is characterized by a creep coefficient, which is just the ratio of measured creep strain to the initial elastic strain. And it's been found to be significantly reduced in UHPC after thermal treatment's been applied. Now this is believed to be due to the collapse in the CSH microstructure during shrinkage, where the CSH phase in cement has actually been found to be the only constituent that contributes to creep in UHPC. And it's also believed to be due to the lack of internal water during hydration during thermal treatment. Now, as with shrinkage, the creep coefficients presented are post-cure, and untreated UHPC would exhibit higher creep strains, more on the range of about 1.2 to 1.8. Now, research on creep of UHPC prior to and during thermal treatment is pretty limited and still ongoing. Now, if we look at the properties of raw materials, mix design, and gradation, those are primarily going to affect the porosity, which can be reduced due to the increased water binder ratio from the addition of superplasticizers. They're going to affect the compressive strength. Now, due to the pozzolanic reactivity of the ground quartz and the silica fume, the reduction in porosity due to the decreased water binder ratio from the addition of superplasticizers, and the optimized particle packing of the constituents, that's going to affect the compressive strength. They're also going to affect the ductility, as would be exhibited by the increased flexural strength, and the post-cracking ductility is increased when the fibers are incorporated in the mixture due to their ability to bridge cracks. Now, due to the ratio of fiber size to maximum aggregate size, it's been shown that each fiber in UHPC is going to react similarly with respect to ductility to a number 3 reinforcing bar in high-performance concrete. Now, that sometimes means you can eliminate the need for shear and flexural reinforcement. So these are going to also affect the durability characteristics, such as freeze-thaw resistance. Now, the low water binder ratio and the dense particle packing contribute to very low permeability, which is the main cause of durability failures in concrete outside of poor material selection and poor construction practices. Creep and shrinkage will also be affected. Now, the reduction in porosity due to the decreased water binder ratio can result in improved creep and shrinkage characteristics. Now, the primary effects of the mixing methods are going to include the compressive strength and the durability characteristics. So if you have less than optimal mixing methods, it can result in an inferior distribution of particles, as I noted before. That'll decrease the desirable effects of particle packing and result in lower compressive strength and decreased durability. So overall, the advantages of the ultra-high performance concrete material include that it's an extremely durable family of concrete, which exhibits high ductility, low porosity, is nearly impermeable, is resistant to leaching and corrosion, and when you thermally treat it, it exhibits virtually no shrinkage and limited creep. Now, the desirable material properties of UHPC create the possibility for a reduced section size and subsequently reduced weight and reduced demand on supporting structures, as well as reduced material use, both in concrete material and reinforcing steel. Now, the photo I'm showing here is always kind of interesting to look at. It compares 4 sections with equivalent load carrying capacity: a reinforced concrete section, pre-stressed concrete, steel, and on the very left, a UHPC section. So you can see kind of visually there the possibility for reduced section size from conventional concrete, as well as reduced steel reinforcing. Now, I also want to note about this photo that I believe those are pre-stressing strands shown in the UHPC. And that's likely just because UHPC is most often considered for precast, but there's really no reason that standard rebar couldn't be used for the UHPC section. So now, though this material has many advantages, it also has a lot of disadvantages. Now, the costs for UHPC have been reported at around 20 times that of normal strength concrete if you compare it unit by unit. But the large reduction in section size that's made possible with the use of UHPC would offset this a bit. The high cement content itself makes it expensive. And then if you look at the finely ground quartz aggregate, that's an aggregate that's less available, so it's going to come at a higher cost. Another disadvantage would be the complexity of the mixing and curing processes. You need specialized equipment and a lot of attention to temperature control, mixing processes, batching. Everything needs to be pretty controlled to attain the properties that UHPC exhibits. So some existing industry applications of UHPC include bridge girders. Now, this is a bridge in Wapello County, Iowa, and if you're familiar with the area, it's near Ottumwa. Now, it's the first UHPC highway bridge constructed in North America. It was built in 2006, it's a 110-foot span, and they were able to use a standard Iowa DOT bulb T girder and then augment that section size from normal strength concrete to apply it to UHPC. So they were able to decrease that section size. Also, due to the presence of the steel fibers in the UHPC mix, the girders didn't require any non-pre-stressed reinforcement or no shear stirrups. Another existing industry application is the use of UHPC for permanent formwork. Now, this is a bridge in Sydney, Australia that was constructed in 2003. It is a highway bridge. It's a 49-foot span, and they did use UHPC for the girders. But the really interesting part is that they also used it as a 1-inch thick permanent formwork into which they just poured the normal strength reinforced concrete deck. Now, that permanent formwork on the underside of the deck can provide protection from damage for the normal strength concrete with the improved durability and high strength of the UHPC. Another existing industry application is the use of UHPC to create more slender elements. And this is a photo of some slender columns that were constructed in a cement silo in Detroit in 2004. So these are 2.5 feet by 2.5 feet square columns. They're about 54 feet high. And they were able to, from an equivalent design with normal strength concrete, they were able to decrease that column cross section by around 75%. And that allowed them to increase the total truck width clearance in the silo by around 5 feet. So the only reinforcing steel present in these columns consists of 4 half-inch diameter pre-stressing strands, and the need for circumferential reinforcement was eliminated with the use of UHPC. So other existing industry applications include the use of UHPC for joint fill and precast bridge decks. And the photo on the left is a bridge in Ontario, Canada that was constructed in 2006, and you can see the joint fill, the UHPC joint fill right here. It's been used for unreinforced shell structures, and the photo in the center is a clinker silo in Illinois built in 2001, and they actually used UHPC for the roof structure. And it's kind of a comparison study that they're monitoring over the years. They had 3 clinker silos. They built one roof with UHPC and the other were built with steel. So they're comparing the durability of those materials, as well as they also compared the construction cost and time. The UHPC was actually constructed faster than the steel roof. So it's also been used for containment vessels for aggressive liquid compounds. And this photo down here on the right, it's kind of hard to see what's going on, but it's a wastewater treatment plant where they made some containment vessels for wastewater treatment. So some possible industry applications would include bridge deck overlays. Now, much like the use of UHPC and its protective capabilities as permanent formwork, you could do the same thing as a bridge deck overlay to protect the underlying structure. You could also use it for protective structures. It's shown a lot of promise in the areas of blast and impact resistance. It could be used as a repair material, as well as a material for use in highly corrosive marine environments. Now, some possible applications that WJE could employ for UHPC could include corrosion protection, structural repairs and retrofits when you might have issues such as space restrictions, durability concerns, or aggressive environments, or for blast resistance improvement. Now, some of the roadblocks that exist with the application of UHPC would be that in the US there aren't any testing or design standards at all at this point. It actually remains undefined in the concrete industry, in the American concrete industry, specifications and standards. So it needs further research and duplication of results. And also, just specifying the material would require a really aggressive quality assurance and quality control program, just to be able to ensure that it's mixed properly, that it's placed properly, and that it's cured properly. These references these are just kind of a long list of some of the references for strength and durability in UHPC. And if you'd like more information on the material, these are great places to start.